Okay, awesome answers up here. Stored energy, really important. We're going to actually find out that stored energy expands into a couple of different ways, not just one type of stored energy. The domino standing up is definitely a type of energy. I'm going to say something. I think we really like to answer our questions with gravity, which tends to be a lot of the answers. But gravity is not a flavor of energy itself. Okay, we want to be really clear that gravity is only an energy when it's talked about in its stored gravitational energy. Right? Gravity is the thing that pulls things down. Gravity is the phenomenon that pulls things to the ground. Okay? So we want to be really clear that just saying gravity is not a type of energy, but the stored gravitational energy through the gravitational field. That's how we need to understand that type of energy. Okay? So from here on out, let's try to change those answers of gravity to stored gravitational energy from here on out. Okay? All right. So a couple of demonstrations today. We're going to analyze and make a couple of the bar graphs, the LOL bar graphs that you're going to be asked to do on the worksheet tonight. We're going to talk about different forms or flavors of energy, and we're going to analyze where they're at different points along this motion. So we're going to start out with an easy one that we did yesterday and see if we can get a good answer here. All right, so here's our starting point. We're going to follow it as it falls down the ramp and off the table. Thank you, Clark. All right, so in your group, I want you to talk for 30 seconds about the different flavors of energy at different points along the ramp and on the table. Go. Let's bring it back. Let's talk first about the system. What are we considering to be our system? What are we choosing to ignore in the classroom? An example of the system is, am I worried about a book that's got energy up on that bookshelf in this classroom right now? No, right? So am I worried about even this thing sitting on the table next to here? No, or my coffee, or these rubber bands, or whatever. We just want to simplify to the only thing we're looking at in this example. What's one thing that we're definitely going to have in our system? The ball. So the ball, we need to follow the ball. What else? What else would be important here? Morgan, what else is a part of the experiment that we did, the little demo I just did? Don't overthink it too much. What was a part of the system? Just anything as a part of the system. The ramp. Great. Steph, what else? What else did it roll on, fall? What was part of it? Table. Great. See, these are not as complicated as you might think. Group in the corner here. What was the initial energy, and what flavor was that initial energy found? Could you give us a little description about when the ball was sitting right here? What was an important part of the energy? In what? It was stored in the ball, but by what kind of sense? Where was the energy stored? What about the ball tells you that there's stored energy in it? You can use some hints on the board that we used. What is special about the ball? Let me make a point here. Just looking at where the ball is at here versus here, what's changed? From this point to this point. What have I increased? Someone want to help them out? What's changed? What is really important about the ball that says there's stored energy in it? Rachel, you got something? There's no velocity yet. It will. We'll get to the movement when we get to the bottom. Right now, no velocity, but it's stored in there's something very specific about where it's at that tells us, Martin's grinning over here, what is it? The height, exactly. The fact that it's up off of the table, the height is greater at this point than it is down here. So remember, we're storing it in the fact that it's up off the ground. What else is really important about it, Martin? What's the other factor? The height and the gravitational field. The gravitational field. So let's actually add that to our list. We're going to make this list today. Stored, we had this from yesterday, we're going to keep adding to it. Stored gravitational energy. And this is often sometimes called the potential. Stored gravitational potential. All right, the two main factors for right now that we're going to focus on are height and the G field. Gravitational field. Ayla, Rachel, Pace, is that making sense now? That the height, when we change the height, that's what changes the gravitational, stored gravitational. Okay. And we'll abbreviate it with capital E for energy and it's lowercase g for gravitational. Alright, so we go over to our chart here. We're going to say E little g. All of our energy there, we're going to put a bar and say, there you go. We definitely have a lot of stored energy. We're making a bar graph here. Okay, just making a bar graph. Okay, let's move forward here. This energy goes through some transfer. It changes how it's being expressed. Here, okay? So, let's just take some very simple observations about what's going to change about the ball. Rachel, I might come to you on this one because you helped us out earlier. Ready? Here it goes. What's happening right when it hits the bottom throughout the table right here? What's different about the ball from up there? Right?
It's no longer gaining anything.
It's no longer gaining anything. Awesome. So it's no longer changing its height. That's a great way to start. So if we've got to the point where it can no longer drop anymore, what do you think we can say about our stored gravitational energy? Is there any room for any more stored gravitational energy in the ball? No. We've lost all of that stored gravitational energy because now we're at this point where it can't drop anymore. So if we go to our final and we say stored gravitational, what's that value going to be? 0, right? We lost all of it. So we'll just put an X here. There's no stored gravitational. Okay, there's another thing I can't really demonstrate it without putting it down here. Notice the difference right here after I let it go versus right here as it's coming across the table. What's the glaring, most obvious thing that's different about the ball? This is the easiest way to notice energy, to see energy. When something's
slowing down.
not slowing down,
It's constant.
we're overthinking it. The easiest way to see energy is when something's
Moving.
moving.
Oh.
When something's moving, okay? So no movement up here. No movement up here. When it's rolling across the table, it's definitely moving. There is a movement energy. And how do we recognize movement energy? Movement. It's the simplest one. If it's moving, it's got energy. If it's moving, it's got energy. And the way we abbreviate that one is E little m, energy of movement. Okay? Awesome. So let's go ahead and add that to our charts here. So if we go over here and say energy movement, was it moving at the start, Javon?
Mm-hmm.
Right when I let it go? Like the second I let it go, was it moving? Yeah. So there's no energy of movement there. When it got down to the table, Shante, what do you think? There's quite a bit of movement, right? We've had a transfer of that energy from the stored gravitational to the energy of movement. Okay? I'm going to put one quick note in here. If we say ignore friction, it's important we need to do that. Ignore friction. If I say ignore friction, which we'll discuss in a second, what can we say about the stored gravitational energy here and the movement energy there? What do you think we could say about those two values?
Not the opposite.
They're not opposite. We're talking about, say they are? They're the same amount. The total amount of energy is conserved in a fixed system. So the gravitational stored energy here is going to be exactly equal to the amount of movement energy at the bottom of the ramp. It's all been switched to this type of movement. The gravitational has been switched to movement. If we made a graph of the ball in the middle of the ramp, we would have a little bit of gravitational still. We'd have a little bit of movement energy. Right? It was being transferred from this to movement energy. Okay, now we're going to give a slightly different example. We're going to add another type of energy. So I'm going to put these towels down here. Okay. At the end of my ramp. Okay, so we got these towels down. And this is going to be a very similar example in some ways. I want you to discuss it with your group though. Okay, here's the demo. I'm going to take a marble up here, and I'm going to set it right here and drop it. Okay, for this one, we're going to make another chart. Let's call it marble on ramp with towels. Okay? And for this one, I'm going to have you do a slightly different graph. We're going to do an initial. We're going to define our system. And then I want you to do two energies. You're going to look at the energy twice after that. So it'll be an initial. And we'll call that point A. And then we'll call this point B and this point C. So I want A to be when the marble is right here at the top. I want B to be right before the marble touched the towels. And I want C to be where the marble stopped there. So go ahead and think with your group about 30 seconds. Talk about what types of energy were present and where some changes were going on, where that energy may have gone.
And then that's
All right, so let me make a note here. In this example, we're not ignoring friction. Do not ignore. Well, that would be a really difficult example if we didn't ignore
No, it
friction.
was funny because we were ignoring it and there's a bunch of friction.
Okay, so Steph, what was our initial energy of the marble? Stored gravitational energy. When I had the ball up here, its height was higher than where it was going to go, so we know that it had some gravitational stored energy. So let's put that on here. Our E little g. Oh, how did I get another bad one? All right. Stored gravitational. There we go. Was it moving at the top?
No.
No movement, so energy of movement gets an X. That's about all we know so far. That's what we're just using here. Let's go to point B. Remember, point B is right before it hits the towels. Morgan, tell me about these two values, the stored gravitational and the energy of movement, when it's at the bottom. We've got movement. What happened? Is there any stored gravitational left? If it's at the very bottom, Remember, there's only stored gravitational and it has the potential to drop more. Can it drop any more when it's down here? Right. We're not going to go off the table. It could go off the table, but we're stopping at the table. So if it can't drop anymore, then it's got no gravitational potential. Okay? So at this point, our EG is nothing. And Morgan said we probably should add some movement energy because she saw that the marble was moving. Okay, that's my bar of movement. Giovanni, what do you notice about the two bars that are up there?
For them both,
Yeah, what do you notice about it?
there's not as much movement as there is potential.
There's not as much movement. Let's be really specific. This doesn't just tell us movement, it tells us the energy associated with movement.
Yeah, and that definition is recognized. So B has less movement energy than A doesn't have potential.
Okay, so Tuplani's noticing that the way I drew it, there's slightly less movement energy as there is gravitational energy. Remember, in this example, we're not ignoring friction. Let me go ahead and put the system in here. We got the marble, the ramp, the towels, and the G field. Okay? So as we go down, we're not ignoring friction anymore. If there's contact between two surfaces, the marble and the ramp, what must be present there? If there's contact between two surfaces, there's always a little bit of friction, right? This actually is not a lot of friction between a metal thing and a marble. But we can kind of hear it even before it gets to the towels, that there was a little bit of friction as it went down the ramp. So, let's be a little more specific. A little bit, how much, if I was to say, this is your information, how much of that friction energy might there be in this system now at point B? Where are you getting that from, Ava? Hold on. So Ava's saying that this is slightly less than this, and whatever that friction energy must be whatever's lacking, right? Like if I was to put this here, you would say that this green box is how much friction energy there should be? Awesome. That's exactly right. This is our little box. Let's go ahead and put a definition to that type of energy. We're going to call this type of energy, and this will be the most abstract, the most difficult to really wrap our heads around, but we're going to spend some time with it. Thermal energy.
Jeez.
Thermal energy is associated with friction and the random movement of particles. Okay? Random movement of particles. And we're going to write that as ETH, energy thermal. So let's put this little guy as ETH. And let's go over here and add it. Was there any thermal energy at the start? Thank you, Joanne. I'm done. Okay. Now, Chante, what do you think happened once the marble hit the towels?
The amount of friction increased.
Yeah, the amount of friction definitely increased. We saw the ball go from having a lot of movement to about a half meter away, completely stopping. This right here, this stretch, was completely a change from movement energy to entirely into thermal energy. When I say the random movement of particles, as the ball rolls through this cushioned set of towels, it's sending its energy out into the towels that are dampening it and taking away its motion energy it's dissipating out into the towels. Like I said, this is a complicated thing. The best way to understand thermal energy is you get down to a particle level, that when two things are in contact with each other, they send the different atoms and the different particles into little vibrations. And that's basically where the energy goes. It vibrates the bonds and the atoms of two things a little quicker, a little faster. Thermal energy. That's about as far as we're going to take thermal energy. But if there's friction present, it's going into thermal energy. If something is moving and it's on a level surface and it stops, it's probably going into some type of thermal energy. So let's finish this one up. If we said for point C where it stops, Eg, Em, and E thermal, is there any gravitational when it stopped? No, it can't drop anymore. Is there any movement when it stopped? No. So, what must be our value of the thermal energy here? Martin, what do you think? How large should that bar be for thermal energy at this point? Was that in the middle?
Yeah.
Okay. If we put it in the middle here,
No, he said all the way.
you said all the way?
Yeah.
You're just helping him out here? Let's say, Martin, let me just, if you said medium in the middle, we'd have to find another place that the energy went,
Oh.
right? And right now, we don't really have any other ways that the energy could have gone into something. So in order to keep true that the total amount of energy is conserved, this bar is going to be exactly the same height as the starting bar that was gravitational. So we just had it go from gravitational to movement energy and a little thermal to entirely thermal energy. Okay, real quick, we're going to shift back into our thinking about that golf ball demonstration. I know, our favorite thing, but hopefully this is where it starts to really click and make sense. That we said the total, the number of golf balls on the table, the number of golf balls on the table was 12, right?
Yes.
And that equaled, we made like a little equation. You guys remember? Let's stay focused up here, guys. Remember the equation we made for the 12 golf balls? That was always the number seen, the number we could see, plus, what else? What did we add to that equation? Remember we were counting up to 12. It was the number we could see, plus the number
In the book.
in the box.
Yep.
Number in the box, plus what?
Water.
Number in the water. So 12 golf balls, 3 different ways we could count them. Always equal 12. Here's our analogy. We have the golf balls represented energy. The total amount of energy, which was the 12 golf balls, the total amount of energy in a fixed system, I'm not going to write that in here, was, what could we see really easily? What kind of energy can we see really easily? Movement, right? So let's call that the movement energy plus storage in the box. Where can we store energy in this system? Where's one way we could store energy? Stored gravitational energy. Thank you, thank you. Plus the stored gravitational energy, plus number in the water, not really the best connection there, but we can say that represents the thermal energy. So we're taking that analogy and applying it to 3 different ways we can calculate energy. Now, if we check, in this system, does this equation always work? The total amount of energy is always equal to the addition of these 3 things. Well, at the start, these 2 are just 0, and so it's just all Eg. In this one, Eg was 0, but Em plus E thermal equaled the total amount again, right? This little green box on there equaled that total amount. Over here, Eg and Em are 0, but E thermal equals
Okay, that little bit.
the total amount. There. Right? So always conserve. Always conserve. There's different, just like we thought, where did the golf balls go? They disappeared, and then we found them some way. That's the same way we think about energy. Oh man, the marble just stopped. The energy must have disappeared. And then we said no. We found it in the fact that it dissipated into these towels through thermal energy. Right? When we hold the golf ball, when we hold the marble up here, we say, oh my gosh, it's got no energy. It's not moving. And we say, no, it's actually stored in the gravitational potential. So, always different ways to find the energy without just seeing it move. We've got another source of energy that we're going to talk about. Whoa, there we go. Very good.
Rest.
So we saw, what did we see the rubber bands do right after it left our hand?
Fly.
Fly. Talk about it in energy. What type of energy did it have?
Movement.
Movement, right?
Movement.
So movement energy, but we know that energy in a fixed system must be conserved. So we have to think, well, if it just started to move, it would never do that just randomly. Where was the energy before it started to move? It's a little challenge question. Actually, talk about it with your group for 15 seconds. Where was the energy before the rubber band started to move?
In the urban.
Tell Mark.
In the urban.
All right. Morgan, I heard some really good things over there. What did you say? Where was the energy before it started to move? Whenever you stretched it. If you take the rubber band and you just have it sitting here without stretched, and you have it, you start to stretch it, do you think we're changing the amount of energy that is in the rubber band?
Yes.
Yeah. It's storing energy within itself. How do we know? Because if I let it go, all of a sudden it's got a huge amount of movement energy. So it must have stored some energy in itself in that moment. So we're going to add that to our list of energies.
Oh, dear.
Stored elastic energy. And we can see this by something that is stretched. What is another way you think that something can change its shape a little bit and store some energy? What's the opposite of stretch? Compress, right? If you compress something, it would store some elastic energy in the compression. So stretched, compressed, we're just going to say change of shape, But there's one very important thing about elasticity. Does anyone know what the formal definition of elasticity is? Something that's elastic. Let me phrase it this way. You have a rubber band and you have a piece of Play-Doh. Which one's elastic? And why?
Rubber band.
Why is it more elastic than a piece of Play-Doh?
I don't know. There's no Play-Doh ribs. Yeah.
Because the Play-Doh won't break? You could probably stretch the Play-Doh about the same. Let's just say you could stretch it the same. What's different about Play-Doh and a rubber band?
Doesn't the rubber band come back?
The rubber band comes back to its original shape. Something that's elastic can be stretched, but it always returns back to its original shape. So you could stretch Play-Doh, but Play-Doh would just stay stretched, right? That would not be a storage of energy in that Play-Doh because it doesn't have that elasticity to pull it back. So it's only stored in something that's elastic. So we have to add stretched, compressed, change of shape, but always returns to original shape. To original shape. Awesome. And the way we write that is capital E with a little e. capital E with a little e. All right, so here's our last demo, and we're not going to have the time to do a full pie chart, bar chart, but we're going to take a look at this situation right here. If the table is our reference point, what type of energy do you think this ball would have right now? If this is our reference, where we're going to kind of reference everything from. What does the ball have?
Oh, it has EG.
It has some gravitational potential because it has height, right?
Yeah.
So, but if we consider this to be our starting point, we're just going to say it has no gravitational energy. We consider this to be our starting point. Now, ask yourself the question. If I reach in and do this, did I increase the energy of the system?
Yeah.
I did. Where is the energy now? Ooh. Where is it, Paisley? It's stored in the rubber bands. You just saw it. It just had a little too much energy in that one. So it's stored in the rubber bands. Now, if I let this go, we see it very quickly transfer into what type of energy? Movement. But almost immediately, what is happening to that movement energy? It's great. Right under gravity, what's happening to it? Give it a more detailed answer. It's getting slower, so where it's losing its movement energy, the movement energy is getting transferred into what type of energy? What is it getting transferred into? Stored gravitational energy. So let's watch it again. Elastic, kinetic in the middle. When it gets to the top, it's going to stop moving. So it has no movement energy. It will all be stored gravitational potential. And then after it gets to the top, it's going to say, well, I got nothing else to do but come back down. So all that gravitational energy is going to start being converted back into kinetic energy as it falls. So you'd see a very quick transfer of almost 4 different energies, 4 different ways of looking at it. Elastic, kinetic, to the top, all gravitational, and as it's coming back down, it's transferring back into kinetic. Bell's going to ring here in a second, but if I bounce it, when it hits the ground, the ball, what's happening to the ball? It's getting a little bit of compression, and then it's getting transferred back into kinetic. Those are going to be examples on the homework, so be sure to look at that. When something's getting compressed or stretched, it's always going into some type of stored elastic